All right, continue with part 3. There will be 10 different parts for this chapter. No, I'm just joking. Today is April Fool's Day, so I was just going to mess with you guys. This is the last part of chapter 7. Part 3, we're going to go and talk about Venus, and then we'll go and talk about the stability of Earth and why is it the only planet that can sustain life. All right. A hothouse word, Venus, 7.4. Our goals of learning for this little subchapter is that, is Venus geologically active? And why is Venus so hot? So when we're looking at the surface of the Venus, we can see different features, especially geological features. We can see so many, craters and impact, even though it is less compared to Moon and Mercury, but it shows some of these, craters that shows a early, long ago impacts of comets and asteroids. It has some volcanoes, and even though it is big, but it's not, as I said, the biggest one is at Mars, but it has some volcanoes. It has some tectonic, activities that shows some stresses from the lower level up to the top levels on the Venus, and erosions on Venus. Photos taken by a lander shows a little erosion on the surface. You can see that what I'm talking about, these things, these features, but they're really, really less. They're really, really not, that much compared to, for example, Earth. So does Venus have plate tectonics? Most of Earth's major geological features can be attributed to the plate tectonics, which gradually remarks Earth's surface. But Venus does not appear to have plate tectonics, but its entire surface seems to have been, repaved 750 million years ago. So, with compared to Earth, no, not really. We don't have plate tectonics on Venus. Why is it so hot? And it has a steady temperature, both for day and night, about 470 degrees Celsius, 730 Kelvin, and 950 Fahrenheit. 950 degrees Fahrenheit, both day and night. So it's because of the greenhouse effects. It's very, very extreme. But the question is, why is the greenhouse effects on Venus is like so much stronger than on the Earth? When you compare, just by comparing the temperature, you can see it's way, way more major effect on the Venus versus the Earth. We'll see why. So Venus has a very thick carbon dioxide atmosphere. And it is thick and dense. And the density is actually 90 times the density of the Earth. So if you, for whatever reason, decide tomorrow to go to Venus, you will be squeezed flat and melted because the pressure is 90 times the pressure of the Earth. So it will, flat you, and then it will melt you because it's 950 degrees Fahrenheit. Greenhouse effects on Venus. The thick carbon dioxide, as we just talked about it, atmosphere produces an extremely strong greenhouse effect. Now, there are in the top, clouds, reflective clouds, as we call them. The top clouds in the atmosphere are called reflective clouds. The reflective clouds contains droplets of the sulfuric acid. Okay. And the uppermost has some fast winds that we don't really know why it's happening, but we know that it exists. We don't really couldn't find a definition for it. Now, I put it under red here because it's very important. Earth escaped this fate because most of its carbon and water are in rocks and oceans. It is not in the atmosphere. It's trapped in the rocks and oceans. So it's to our benefit, because otherwise we will be just like Venus, maybe even warmer. So let's take a look. So Earth has a small greenhouse effect. It is in equilibrium with a comfortable temperature. The coming light, visible light come in, hit the ground. It will be absorbed by the ground. Some of it will be reflected through radiation, thermal radiation in an infrared wavelength. This infrared wavelength will be absorbed by these molecules in the down atmosphere, okay, in the lower atmosphere. It will be passed through another molecule to another molecule, and then some of it will eventually spread to the, will be radiated to the space. When you're coming to the Venus atmosphere is way thicker, okay, and the runaway greenhouse effects has resulted in a temperature of 730 K. It almost nothing will go away. Almost nothing will be radiated away from the Venus. So whatever that's coming in will be trapped. And keep that in mind, Venus is much closer. Venus is about, if you consider the distance from Earth to Sun being 1 AU, Venus is at 0.7. So it's very close to the, much closer to the Sun. So that's why it's actually much warmer as well. But not only that, the main reason behind this huge temperature is that the greenhouse effect, this thick layer of the atmosphere, does not let anything to go out. Let's take a look. What would happen on Earth if we had the same thing? If Earth moved to Venus orbit, so we would have more intense sunlight coming in. So that would raise surface temperature by about 30 degrees. Right now, the average surface temperature on Earth is 15 degrees Celsius, 1.5, okay? If we go closer to the point where the Venus is, the average temperature will rise up to 30 degrees. That means high temperature increase evaporation, and warmer air hold more water vapor. So the water will be vaporized, turned to gas. It'll, as you know, we talked about it, but water is one of the, H2O is one of the greenhouse gases. That means additional water vapor further strengthens the greenhouse effect, because now it's vaporized, it's gas in the atmosphere. It will hold the infrared wavelength. It does not let the infrared radiation to go back to the space. It'll hold it in the atmosphere, meaning that it will result, the result is that oceans evaporate and carbonated the rocks decompose, releasing the CO2. Okay, so now that all the oceans are gone, the carbonate rocks decompose, releasing the CO2. And what the CO2 does, I am glad you're thinking about it. CO2 is another greenhouse gas, which means the temperature will go back. The temperature will go up again, because CO2 now it's in the atmosphere along with water, so making Earth even hotter than Venus. So, so the runaway greenhouse effect would account for why the Venus has, so little water, because it's all gone in the atmosphere. The other thing that I want to talk about, I'm really glad that we're not at the Venus orbit, because otherwise we'll be just, we'll all be gone. We couldn't survive the 950 degrees Fahrenheit. Thought question for you: what is the main reason Venus is hotter than Earth? Take a look at these options. Venus is closer to the Sun than Earth. Venus is more reflective than Earth. Venus is less reflective than Earth. The greenhouse effect is much stronger on Venus than on Earth. Human activity had led to declining temperature on Earth. The answer is D. The greenhouse effect, as we just talked about, is very extreme on Venus compared to Earth. When you're looking at some of these features on Venus, when you're looking at them, they look like they're snow, but they're not. So the temperature is hot enough that they can, vaporize the metal. Now this metal can condense and cool down on top of the mountains, and since they're cooled down and condensed, they are shiny. looking like snow, but they're not really snow. Things that we learned about Venus is that is Venus geologically active? Is it active right now? Its surface shows that evidence of major volcanoes and tectonics during the last billion years. There is no evidence of erosion or plate tectonic. We don't really know because we don't see any evidence of it. Why is Venus so hot? The runaway greenhouse effect and made Venus too hot for liquid water or liquid ocean. All carbon dioxide remains in the atmosphere, leading to a huge greenhouse effect. All right, I think this is the last part of this chapter. Earth as a living planet. Our goals of learning. What unique features of Earth are important for human life? How is human activity changing our planet? What makes a planet habitable? Let's take a look. So, four very importantly and equally important, factors. First is surface liquid water. Earth distance from the sun and moderate greenhouse. It's not extreme. It's not really low like Mars. It's in the moderate region. So moderate greenhouse effects make liquid water possible. If we were so far away like Mars, we couldn't have enough greenhouse effect. If we were so close, like where the Venus is, we would have a huge greenhouse effects. So we are in a moderate regime, okay? 2, atmospheric oxygen. Photosynthesis, which what the plants does, right? Plant do, is required to make high concentration of oxygen molecule, which produces the protective layer of ozone. So we need oxygen, not only because we breathe in the oxygen, but also because we need a layer of protection from UV light. 3, plate tectonics. Plate tectonics is an important step in the carbon dioxide cycle. We just talked about it. And 4, climate stability. I'm going to go extensively into number 4 now and talk about climate stability. If you have any questions about this particular one, make sure to email me. Let's see. So when you're looking at our continents, they are moving. We all know that, not just because we're looking at them, but because the GPS can track their motion. Motion of the continents can be measured with the GPS, all right? Now, the first idea of this drift was inspired by the puzzle-like fit to the continent. So we think that they had this beautiful fit, like South America is perfectly fitting Africa. But not only that, but also this. So the seafloor recycling process, I'm going to go and talk about this in a little bit, but when you're looking at the surface of the Earth, we see some very interesting things that are happening. They happen very slowly, but they are happening. So the seafloor crust, which is, let's say, right down here, it will get denser, so it will eventually go down, okay, because it's lower down, so it's warmer, so it will go, it becomes denser and go further down. Oops, okay. And then, which we call it the subduction process, okay? Once it's going down, it is creating more material and, ejecting more material to the convection cell or to the mantle. This extra area, okay, this extra stuff will eventually have to come out at some point, either through a volcano, or it can create and, ridge in the bottom of the ocean, for example. So the new seafloor will eventually create it because of this this phenomena. Okay. So just make sure to understand what we're talking about. Since this is going down to the mantle, we have volcanoes at some point, and then this extra pressure is creating more, you know, crust, the dry crust, right? Pretty simple. Remember the cycle. The cycle is about 100 million years, so it's a very, very slow cycle. But you know, it is happening, even though it's very slow. So these plates motion that we were just talking about, 200 million years ago, it looked like this. 120 million years ago, it looked like that. In present day, on the map of the world that we all familiar with, and in 100 million years, 150 million years from now, it will look like that. Okay, another very important feature on Earth, carbon dioxide cycle. Very, very important. I want you to be able to explain these 5 steps thoroughly in a test, okay? So first, the atmosphere CO2 dissolve in the rainwater, okay? The atmosphere CO2 dissolve in the rainwater. Atmosphere CO2 dissolve in the rainwater like that. And then rain rods, minerals that flow into the ocean. So they will all come to the ocean. Minerals combine with carbon to make rocks and ocean floor. Okay. Ocean floor subduction is what we just talked about it here. Remember, subduction. It's going down to the mantle, beneath another, beneath the lithosphere. So subduction carries carbonate rocks down into the mantle. Now, this bottom of the ocean is carbonated, okay, carbonate. These carbonate rocks will go through the subduction process, going all the way down, okay? Now, what's happening is that these rocks will melt in the mantle and outgas CO2 back in the atmosphere through a volcanic eruption. So, rain bring the through the river, bring the carbon to the ocean, and subduction happens, going to the mantle. This will come back to the atmosphere through volcanic eruptions. A long-term climate change on Earth, or if we have any other planet that they can sustain life in the whole universe, and we're talking about 100 billions and billions of galaxies and billions of billions of stars and planets. We're not just talking about Earth. If there is another planet with the sustainable features who can sustain life, we're talking about that as well. But a long-term climate change which might happen on Earth. Change in the Earth axis tilt might lead to ice age. Okay, so widespread ice tends to lower the global temperature by increasing the Earth's reflectivity. So if the ice age happen, the global temperature will, change because now this ice this ice age that's covering all the planet will lower the temperature because the reflectivity is increasing, so it will reflect everything, almost all the sunlight that it's absorbing, and it's going to reflect it. It doesn't let anything to pass through, so the temperature will drop. Now CO2 from the outgassing will build up will build if the oceans are frozen, ultimately raising global temperature again. Does that make sense? I think I explained it a little bit bad here, or I was speaking too fast. So if the Earth axis tilt change, it's currently at 23 degrees, but if it change, it'll cause an ice age. If the ice age happen, it will cause to lower the temperature because the reflectivity is going high. The Earth is reflecting much more light compared to before, so it's cooling down. Now, if that happens, CO2 from the outgassing of these volcanic eruptions will build up. If oceans are frozen because of the temperature, ultimately, these CO2 ultimately raising the global temperature back again. So it looks like a cycle. So the CO2 cycle, back to number 4, climate stability. The CO2 cycle acts like a thermostat for Earth temperature, okay? I want you to remember and memorize these 4 steps, okay? Very important. These unique features are intertwined, okay? Plate tectonics create climate stability. Climate stability allows liquid water. Liquid water is necessary for life. Life is necessary for atmosphere oxygen, okay? I'm going to ask this question at the end and the last slide one more time. How is human activity changing our planet? Oh, this is so sad. And if I speak more than a few minutes about this, I'll just, lose my temper, because us humans are destroying the planet. We are destroying this sustainability of this planet. This is just like so sad to me to see the global temperature rise by 1 degree at the end of 2020. This is so really bad effects for the future generation. So when you're looking from 1880 all the way to like 1970s or 1980s, the temperature was pretty much steady. Did not change at all. This is the change in the temperature, by the way. It's not the temperature, it's the change in the temperature. So it did not change at all. But right down here, right around like 2000 and after that, look what happened. Like in 2020, it's probably even more than 1.1. It's probably about like 1.2 or so. And that's the average change in the temperature. It means it's covering everything all the way from North Pole to South Pole. Dangers of human activity. Dangers of human activity. We're really dangerous for the planet, being honest. Human activities destroy ozone, reducing protection of the UV radiation. Human activity is driving many other species to extinction, of course. And human activities, human use of fossil fuels produces greenhouse gases that cause global warming. Earth's average temperature has increased by 0.5 Celsius in the past 50 years. Put an emphasis on it. It's probably even more, but we just don't want to scare people. The concentration of CO2 is rising rapidly, and an unchecked rise in the greenhouse gases will eventually lead to global warming. So CO2 concentration has increased. So if you're looking at this, we are in 2020, we're down here. We have more data, but even up to 2010, you can see how much it has increased over the past, probably century, which is actually very sad. Most of the CO2 increase has happened in the past 50 years, but it's continuously being in increasing shape or increasing trend. If we model the climate change, so if you're looking at this figure, the computer model including the only solar and volcanic change, which is this blue curve, this blue one right here, it's only due to the solar and volcanic changes. But if we add the human activities, if we add the human activities in which we are causing the greenhouse effects and greenhouse gases, which is this red curve, which is this red line, and if we add them up to create this black line, it will be perfectly matching what is exactly happening. So we create a computer model to tell us, what's happening, and then the human activity, the red, the solar and volcanic activity add up to create this black one, which is perfectly matching our, measured data, which is actually very sad. Now, what the consequences is that increase in the temperature can be vary from place to place. It has most effects on a lot of places compared to, in different places, depend on where it's at. where you're at, the climate change and you know, the global warming has the most effect. The sad part of this is that it has the most effect on the North Pole. See this red area? It means it has increased over two degrees. So all of the almost North Pole is covered with red. It means that all of those ice, you know, trapped in the North Pole will be melted. That means that the sea level and oceans will you know, increase, and that means we, you know, everything will change. Cities and, you know, states and countries near the ocean will be flooded in the next 50 or 100 years. So increase in the temperature, as I said, vary from place to place, and effect on weather patterns are quite complex. So what makes a planet habitable? We know that we are in a habitable zone. If we were too close to the sun, the surface is too hot to rain and the snow or ice, so little erosion occur. And the high temperature allows the gas to escape more, you know, easily. We are obviously right in the middle, where everything is, you know, stable. Moderate surface temperature allows the oceans to rain, to snow, and you know, and the gravity can, you know, hold the atmosphere. So we're not going to lose the atmosphere because of the gravity of the planet. And then if we were really far away, like where the Mars is, low surface temperature can allow you know, ice and snow, but does not let rain to occur. So erosion will be limited, but the atmosphere may exist, but gas can more easily condense to make surface ice. As I said, greenhouse effect is not really that bad. It's bad if it's too much. It's also bad if it's very less. Have the image of Venus and Mars. Venus has a lot of extreme greenhouse gases and effects. Mars has less. So if it's less or if it's very extreme, it's bad. If it's moderate, if it's like in the right, you know, right limit, it's good. Take a look at this. I just want to specifically point out Earth here. So Earth, the average distance is 1 AU, okay? We're 1 AU from the sun. Reflectivity is about 30%. And if it did not have greenhouse at all, if it didn't have greenhouse at all, our average surface temperature will be minus 16 degrees Celsius, which is probably negative in Fahrenheit. Right now, with the greenhouse effects and the gases that we have in our atmosphere, it's about 15 degrees, okay? Even though it's a little bit warmer now, it's about 16 because of the greenhouse effect has increased it. Okay, and then greenhouse, you know, warming, actual temperature minus no greenhouse temperature would be 31 degrees. So note that how cold Earth would be if there were no greenhouse gas. And also remember this, too much of a good thing can be deadly, just like Venus. Not only we need that, but we also need a right size, okay? Remember, small terrestrial planets like Mercury are geologically dead. So we have to have a right size to be able to be geologically active. If you're really small, we would be geologically dead. Remember this ratio that we talked about? 3 over R. This R, if it's high, this whole ratio is low. So meaning that we're not losing heat with a very fast, you know, speed, with a very fast rate. And that's actually a very good thing. We talked about it, I think, in part 1. So we have to have a right size as well, which Earth obviously has a right size. Okay, So when we're looking at these terrestrial planets, Earth, Venus, Mars, and Mercury, I'm also putting Moon there because it's in the book. But so it was when it was formed, when they were formed in the early history of the solar system, 4.6 billion years ago, they were getting heavily bombarded by these asteroids and comets. As they moved on, tectonic activity and volcanic activity, which is this orange color, Earth kept it all the way up to the present time. Venus has it. We don't really know if it lost it or it got in decrease in the past million year or so. But Mars, as we know, eventually ended up not having any activity because it lost its magnetic field. Mercury and Moon are dead right now. They were active probably about 1 billion years after their formation, but they are completely dead now. What have we learned is that what unique features of Earth are important for life. Most important is surface liquid water, atmospheric oxygen, plate tectonic, and climate stability. How is human activity changing our planet? Human activity is releasing carbon dioxide into the Earth's atmosphere, increasing the greenhouse effect and producing global warming. What makes the planet habitable? Earth's distance from the sun allows for liquid water on the Earth's surface. Earth's size allows it to retain the atmosphere and enough internal heat to drive geological activity. So remember this 3/r one more time. This is very important. It's probably the most important, one of the most important parts of this chapter. This R for our Earth is really, really at the right age, the right, range. R for Earth is 6,400 kilometers. Sorry for my bad handwriting. Okay. So I want to ask you this question, and I want you to spend time, think about it, and I want you to say, what you think about this in a discussion page that I have created in the Blackboard. If you're not doing this, that means that you have not watched the video lectures. That to me means that you are not being present in a class, and I don't like that, okay? So the unique features are intertwined. Plate tectonic create climate stability. Climate stability allows liquid water. Liquid water is necessary for life. Life is necessary for atmospheric oxygen, which means that you have a UV protection because of the ozone. Now, how many other connections between these can you think of? I want you to think about it, do a little bit of an internet search, and I want you, to talk about it in the discussion. If you really don't know, just go and see what other people are talking about, okay? Go and do a little bit of a search to see what you can find on the relation between these four, and come and, just say hi, or just say something about this. But I want you to say something. I want you to be present, meaning that this way that you have been present in my class, okay? Very, very important. Regarding homework, I'll post homework by the end of today. Today is Wednesday, so I want you to, watch, as I said in part one, watch the video lectures at the same day of the class. But the good thing about these recorded video lectures is that you can watch them at any time in the future. So go ahead and talk about this question in the discussion forum, in the discussion webpage on Blackboard. You can see it on. I might take a screenshot and post it on Blackboard. But anyway, go ahead and talk about it, and I'll post homework soon. It'll be just multiple choice questions, just like what we had before. And you have 1 week to submit. Make sure that if you're submitting, I want the images to be very high quality so I can read them. And if you have any questions, again, today is my office hours. Today, Wednesday, my office hours is from 3:30 to 5:30, just before the class. I have sent you the Zoom invitation, so you might have it. Come and talk if you have any questions or concerns. You can come and talk with me, and I'll talk to you soon.